We're going to kick off the year with a review of functions. And so in this video, I'm just going to go through and do some examples highlighting some of the concepts that are mentioned in the first reading that you'll do in lesson 1-1. So let's get right down to business and tackle some examples. We start out by looking at some relations, and we want to identify the domain and the range of these relations. So you can see that's asked right here. And then also decide if these are functions. So hopefully you remember that when data is organized in a table, and especially when it's labeled X and Y, the set with the X label is our domain. And in this case, our domain is -3, -2, -1, 0, 1, 2, and 3. And I'm just going to list those here. And that's the domain for this particular relation. Now, the range is the associated Y value for each of those. These are the range values. That's an N. So the range is, you can see there's a 1, 4, 9, 0, and then a 1, 4, 9. So I'm going to say 0, 1, 4, and 9. And that's the range. And then to decide if this is a function, we need to draw some arrows to match these ordered pairs up. So -3 is matched with 9. -2 is matched with 4. -1 is matched with 1. 0 is matched with 0. 1 is matched with 1. 2 is matched with 4. And 3 is matched with 9. Now, the way we decide if this is a function or not is we look at each value in the domain and make sure it only has one match in the range. So I take a look at -3. How many values are matched with -3? Well, it's just one. It's that 9 right there. And -2 has one match, which is the 4. -1 has a match, which is the 1, and so on. And you can see in my diagram here that this is a function because each value in the domain is only matched with one value in the range. Notice it's okay if these range values are matched with more than one domain value. So 9 happens to be the Y value for both -3 and 3. That's okay. In order to be a function, the range can be used more than once, but the domain can only be matched with one value in the range. So that's the deal on these problems. And you can see when we move on, I just did number 1 there. And when you move on to do some of the other exercises, you'll just basically look at the same 3 parts. List the domain, list the range, and then decide if it's a function. Once you've worked with domain and range, you're going to be asked to evaluate some functions. So I just want to remind you what this notation means. We are asked to evaluate in letter A for each of these problems, f of, and then there's a 0 in the parentheses. And what this means is take the function f and plug 0 wherever the x is in the function. So for us, that means 5 times 0. Notice I put whatever was in the parentheses in the function notation here. I used parentheses to replace the x there. That's important because if there's an expression with more than one term in your where the x goes in your notation, you'll have to replace that x with the entire expression. Now let's just finish this one off. It's 5 times 0 minus 2. And then when you evaluate that, that works out to be 0 minus 2, which is -2. So my answer for letter A is -2. And we're just going to run through this process for each of these values. So it's going to be, for letter B here, f of 1, it's going to be 5 times 1 minus 2, oops, not equals, how about minus? 5 times 1 minus 2 is 3, so there's my answer for that one. For letter C, 5 times 3 minus 2, that's going to be 15 minus 2, which is 13. So those first 3 answers were pretty straightforward. Just a little bit of arithmetic there, and we were able to handle it. Now, let's keep going here. Letter D, we want to do f of the opposite of x. We're going to actually put -x in there. I want to write this out so you can see it with a little color. I have to put that negative x, or that opposite of x, in wherever I see x. I'm running out of space here, so I'm going to do 5 parentheses, negative x minus 2. And then simplify this, I get negative 5x minus 2. That's as far as I can go, right? These are not like terms. There's no other arithmetic I can do. So I have to just stop here. Notice it's okay if my answer is an expression, right? If my function is being given an expression, you're probably going to get an expression with variables. This is a variable expression for your result. We just had integers for the first answers. Letter E, we're trying to compute f of a, and all we're saying is take the letter a and put it where x is. So for letter E, it's simply going to be 5a minus 2. This is an a. And then finally for letter F, there's an expression with 2 terms, right? That's a binomial. So we just have to be careful how we plug that in. I'm going to write that right along the bottom here. For letter F, it's 5 times a plus h. You have to put that in parentheses because eventually when we simplify this, we're going to distribute that. So 5 times a plus h minus 2. And then when we distribute, we get 5a plus 5h minus 2. None of those are like terms, so there's no more simplifying we can do. And then this expression is our answer for that one. We're really just practicing function notation here, which you've used before, but just reminding you, and you'll have some exercises where you have to do that. In the next set of exercises, we're given a list of functions. Like in number 14, we have f of x, and number 15, we have g of x. And we're asked to find the domain, the range, and any zeros or intercepts. So let's go ahead and do that. And I'm going to start with number 14 here. 14 happens to be a rational function. Let's talk about domain and range. So if I factor this denominator, I'll find out that there are 2 values that will not work in this function. Right? Since x squared minus 16 is a difference of perfect squares, it factors as x minus 4 and x plus 4. So I cannot have a 4 and I cannot have a negative 4 in this function. We will get undefined values for this function if we plug in 4 or negative 4. So the domain is everything except for x equals 4 and x equals negative 4. So we'll say all reals except 4 and negative 4. That's how I'd write it in English. If I was going to write it in interval notation, which you'll be working with eventually, I would write it like this. Negative infinity all the way up to negative 4. I would union that together with everything between negative 4 and 4. And I would union that with everything bigger than 4. We'll talk more about interval notation as the class progresses. For the range, we're looking at the y values and what y values this function attains. The best way for us to get a quick answer on that is to actually look at the graph of the function. So I've gone ahead and graphed this function using Desmos, and I'll show you that on the next slide. So you can see here that I've drawn the graph simply by typing the function into Desmos, and it made the picture over here, which is pretty cool. You can see that those undefined values that we named at negative 4 and 4 are the asymptotes here. We cannot use those x values to get a y value for this function. All of the other x values, we do get y values. Now, when talking about those y values, we want to know which y values we hit. Well, as you can see, we're definitely going to hit all the positive y values. We're definitely going to hit all of the negative y values down here at the bottom. And in fact, even though we don't hit 0 here, we do hit 0 at the origin. So the range for this function is all real numbers. In set notation, you just put a capital R, or you might say x is an element of the reals. But in interval notation, we're just going to say our range goes from negative infinity all the way up to infinity. That means our function hits every y value there is. There's an x somewhere that hits every y value. We were also asked to find the zeros or intercepts. So let's talk about zeros first. We just circled one of the zeros, and that's right here, and you'll see there's nowhere else that we hit the x-axis, so the only zero we have for this function is x equals 0. That's where y equals 0. In terms of intercepts, that 0 is the x-intercept. There are no other x-intercepts because these are asymptotes, right? They're horizontal asymptotes. And that 0 is also the y-intercept. That's the only place we hit the y-axis. So I'm going to go ahead and say the y-intercept is 0, just to state it. But since we identified that 0, it turns out this one happens to be the same spot. In general, when you're finding intercepts, you're looking for places where your function crosses either the x-axis or the y-axis. It just so happens that in this weird function, this rational function, x over x squared minus 16, it only crosses the x-axis at the origin, and it only crosses the y-axis at the origin. Okay, so we went through and we actually answered all the questions. We did the domain, the range, the zeros, and the intercepts. So we've tackled everything for that one. Feel free to use the graphing tool to help you investigate the other functions in that group of exercises. Absolutely a useful tool. Recommend that you use it. In the next set of exercises, you're going to be sketching some graphs. So let's just talk about that word sketch. Sketch means you want to get a hand-drawn picture that pretty much looks like the function. And that's all that we're going to look for. You are, in each of these problems, you're actually given a table of values, which makes it a lot easier. So when we talk about a sketch, here's what we're talking about. You're going to actually draw a coordinate plane with a set of axes. The x-axis and the y-axis should be labeled, and they should have arrows at each end of those axes. And then you're going to want to put some tick marks on to indicate some values. You can either put those on now or later. I just want to see what we've got here. So I'm basically going from -3 to 3 on my x-axis. So I can space these out a little bit better. 1, 2, 3, -1, -2, -3. Put some labels on there so we know the scale. Now, on my y-axis, I have to be careful. I go up to 10 and up to 10, but the lowest I get to is 1. So, truth be told, I'm not going to need the bottom part of my axis. I'll still put some labels on it, but I need to get all the way from 0 up to 10 on this y-axis. So I think it'll be a good idea if I just count by 5s here. So I'll put a 5 here, I'll put a 10 here, and that means I have to put a -5 and a -10 down here. I'm just making a sketch, remember. Okay, now we're going to plot these points. So at -3, I'm up at 10. At -2, I'm at 5. At -1, I'm at 2, which is probably about right here. And at 0, I'm at 1. Then we're going to move up again, because it turns out this is just a parabola shifted up 1. So there's 1, 2, here's 2, 5, and there's 3, 10. Don't panic about whether or not you have this vertex point exactly in the right spot. It's a sketch. And then all you're going to do is actually draw your function through these dots. And then remember that even though we haven't drawn it, this function keeps going. Okay? So that's a sketch. Take your time on the sketch. Notice my handwriting's not great, but the graph looks pretty neat. And that's what I'm expecting from you. It doesn't need to be a work of art, but it does need to represent the function enough so that we can tell what it is. Okay, that's what you do for that set of problems. In the next set of problems, we're just going to be reviewing some other aspects or characteristics of the graphs of functions. So you'll have to answer A through H for each of the graphs that you're investigating. Here I'm going to take a look at number 30. You can see it's a parabola, it's opening downward. And then we're just going to go through and answer the questions for these. So for letter A, we know this is a quadratic function just based on what we see here. So you should remember that the domain for quadratic functions is all the real numbers, we'll use interval notation and just say negative infinity up to infinity. That's how we communicate that we're having all real numbers. Now, for the range, we want to talk about the y values. And while this function hits all the y values that go down towards negative infinity, it does not get past 3. So when we list the range, we want to make sure we indicate that. So for our range, the lowest it goes is negative infinity, but the highest it goes is 3. And because it hits 3, instead of a parentheses in this interval, we're going to use a square bracket. Whenever we include some kind of infinity in our interval notation, we use parentheses. You also use parentheses when the value that you're approaching is not included. But since our vertex here is at 2, 3, we want to include that y value in our range. And that's why I'm using this square bracket, because 3 is actually in the range. It's not just a boundary. Okay, let's move on. For letter B, do we have any x-intercepts? Yeah, we've got one here, and we've got one here. And I'm just going to call that, we have to estimate, let's say 0.2. So x equals 0.2, and how about 3.8? The y-intercept is right here at -1. So I'm going to do that for letter C. Is x equals 0, or I'll put 0, -1 for the ordered pair. How about that? The y-intercept's at 0, -1. The intervals where the function is increasing. So increasing, in case you don't know what that means, increasing means moving upward from left to right. So as I start over here on the left and I work my way to the right, moving in this direction, the place on the graph where this thing is moving upward is right here. This is called increasing. And in interval notation, the way we indicate that is we say we're starting over here at the left, which is negative infinity, and it increases all the way up until this x value right here at x equals 2. It's not increasing or decreasing at 2, so we're not going to include that with a square bracket. We're just going to put that interval where it's increasing. 2 is the boundary where it stops increasing. Similarly, decreasing would be the places where this thing is heading downward from left to right. So as I move from left to right, here's the places where the function's moving downward, which is decreasing. So for letter E, we're going to start at 2, and then we'll work towards positive infinity. And remember, these intervals, when they mention intervals, they are talking about x values, the intervals where the function's increasing, the intervals where it's decreasing. We don't have any intervals in this function where the function's constant. Okay, so because what I'd be looking for is places on the graph that are flat like this. This graph is always curving. It's either curving up or down, but it's not constant. So for letter F, we're going to say none, because it doesn't happen to have any constant sections. Symmetry about an axis or the origin. So this function does have symmetry. It has a symmetry about the line x equals 2, right? About this vertical line x equals 2. So this is x equals 2. And you can see that there's some symmetry here because it can reflect across x equals 2. So I will say it's a reflection across x equals 2 for letter G. It's probably been a while since you talked about that, but that is something that you discuss in algebra. And then finally for letter H, whether or not this function is even or odd. So here's how this works. A function is even if you get the same y value when you plug in the positive value and its opposite. So for example, what is the y value at -1, for example? Well, for -1, it's way down here somewhere, right? Below -5. So maybe -6 or -7. For +1, the y value is up here at 2. So this function is not even So I'm going to put even and then draw a big line through it, because f of negative 1 is not the same as f of 1. A function's odd if, when you plug in negative x instead of x, you get the opposite y value. So for example, we just said when I plug 1 in, I get 2. If that function were odd, then I would get negative 2 when I plugged in negative 1. And we know that's not the case, right? The y value is way down here somewhere around negative 6. So this function is not odd either. In that case, I'm going to say for letter H that this is neither. Let me write out some math notation to drive that point about even or odd functions home on the next slide. Just to be clear, a function is even if f of x is equal to f of negative x. For example, if the function was just f of x equals x squared, this function is even because f of negative 2 is 4, and so is f of 2. So both f of negative 2 and f of 2 equals 4, and that works for any opposites. F of 3 is 9, f of negative 3 is 9, f of negative 5 is 25, f of 5 is 25. That's what we mean when we say even. A function is odd if f of negative x is the opposite of f of x. So for example, f of x equals x cubed is an odd function, because if I do something like f of negative 2, I get negative 8, because negative 2 times negative 2 times negative 2 is negative 8. And f of 2 is positive 8, because 2 times 2 times 2 is 8. So these guys are opposites, right? These function values are opposites when we plug in the opposites. That's what odd means. And then if either of these fails, or excuse me, if both of these fail, then you just say that they are neither even nor odd. Okay, that was a little explanation for even and odd. Let's move on to the next set of exercises. Everything greater, oops. So we're going to go back to Algebra 2 for a little bit of arithmetic with some functions. In these problems, you're given functions f and g, and then we're going to do addition, subtraction, multiplication, and division with these functions. And then we'll examine the domain and range, or just the domain, to see if anything falls apart on these. You'll have to have an idea of your families of functions and what their domains are. For example, in number 36 here, the domain for f, since it's linear, is all real numbers. The domain for g, since it's linear, is all real numbers. And then we'll see what happens when we combine these functions. So for a, we have to do f plus g. All you're going to do is add together 3x plus 4 plus x minus 2. 3x plus 4 plus x minus 2. And I'm going to combine like terms and get 4x minus 2. The domain is still all real numbers on this one because it's still linear. Let's try f minus g. Oops. I'm going to use a little bit better notation on this. I should really put f minus g of x like that. So f minus g is going to be 3x plus 4 when you subtract a quantity, like in this case a binomial like x minus 2, you have to put it in parentheses and distribute that negative sign. So this is going to be negative x plus 2. And then I'll combine like terms, and I'm going to get 2x plus 6, which is still linear, and still the domain is all real numbers. The next thing we're supposed to do is multiply these functions. And so just remember, when you're multiplying two binomials, we usually write it like this, and then we'll use the distributive property, which many of you like to use the shortcut called FOIL to distribute. And when we do that, we get, let's write all these out here. It's going to be 3x squared minus 6x plus 4x. That's going to be minus 2x. And then minus 8. This is a quadratic, and a quadratic, the domain is all real numbers, so we're okay there. Our last function is f divided by g of x. And in this case, we're going to put 3x plus 4 on top in the numerator and x minus 2 on bottom in the denominator. Now, in this case, we have a rational function, and rational functions may have undefined values. In this case, down here, when x equals 2, the function fails. There is no y value. So we need to exclude 2 from our domain. So our domain is going to be all the real numbers except 2. If you want to practice your interval notation, that would be negative infinity all the way up to 2. And then use a parentheses because 2 is not included. I'm going to make that a better parentheses. And then when we want to put it together with the other part of the interval, we use a u for union. And then we say we're going to pick up where we left off at 2 and go all the way to infinity. Notice in this notation, because we have these parentheses here, for that 2 is not included, and here this 2 is not included either. That's how we achieve communicating that we don't want to include 2. Okay, so in general, we're going to add, subtract, multiply, and divide our functions. Usually you need to be a little bit careful when you're multiplying functions, or excuse me, dividing functions, because you may run into some undefined values. The other thing I want to point out to you, if you get down here to number 40, notice there is a square root function. F of x is the square root of x. The square root of x has its own domain, right? We can't square root negative numbers. So the domain for the square root of x already starts out to be everything greater than or equal to 0. So that what I meant to do is this. Now I don't know what I've done. All right, here we go. So our interval notation looks like this when we do that. So just be careful. For our linear functions like we had in number 36, our domain started out as all real numbers. But some of these problems will have limited domains. Same thing down here in number 41. X can't be 0 when the function's 1 over x. So just be careful of that. All right, last one coming up here. We're also going to have some applications where there are words in the problem. You might call these story problems. And so I just want you to be aware that this is an important piece of what we're going to do, and it's great for us to practice this. So we'll start here by reading the statement of the problem and then looking at letter A and letter B to see what it is we're asked to do. The statement is that the volume of a cube depends on the length of the sides S. And what we're asked to do is write a function v of s for the volume of a cube. So what we're saying is, in math notation, we want to write what that sentence says. So for letter A, we're going to write our function, which is v of s, and then we want to define it using an expression involving s. Well, up here, we're told that the volume depends on s. It's a cube, so hopefully you remember that you take the side and you cube it to get the volume. That is a fact from geometry. So I'm just going to write down the letter s, which is my side length, and I will cube it to compute the volume. And then for letter B here, we want to find v of 11.8, meaning we are supposed to cube 11.8. So we're actually asked to find that, and then we'll talk about what that means. That's what interpret means. Because this problem has this little T indicator here, that's their way of saying that they want you to use some kind of technology, meaning a calculator. And so I've gone ahead and done that. When I cubed 11.8, I ended up with 1,643.032. And we'll go ahead and we will round off our problems to 3 decimal places or thousandths when we do this. In this case, I didn't have to round it. But it may be possible that you'll have to round. It may be required that you'll round. Okay, so we found the value. What does it mean? Well, it means if our units of measure were, let's say, inches. So if the side was 11.8 inches, almost a foot, right? If we're in inches for the measurement of S, then this volume is measured in inches cubed. And that is the amount of space inside the cube. Three-dimensional space inside the cube that this cube can, if we were going to pour water in it, it would do that many cubic inches, I guess what I'm saying, 1,643. I think I really need to stop this video while I'm ahead because it's deteriorating quickly. So we went through a bunch of examples here. It'll probably take us a couple days to get through all of these exercises, and that's fine. But we're really looking to get into remembering functions and function notation by practicing these exercises. You know where to find me if you have questions, and please feel free to ask. And good luck completing these. Take care.